Okay, so now we're going to look at a bit more complicated situation when it comes to gas stoichiometry type problems. So what we'll be combining in this case is what we learned about the ideal gas equation when it comes to reaction stoichiometry. So going back to the law that we just looked at, the law of combining volumes, that only works, as I said before, if the gases that are involved in the reaction are at the same temperature and pressure. But of course, that's not always going to be the case, and therefore we have to use stoichiometric methods that we learned from chapter 3, plus what we are learning now concerning the ideal gas law or equation. So, if you remember, when it comes to stoichiometric reactions, remember we talked about the fact that we need to find the moles of one substance, use the mole ratio based on the balanced equation, and then multiply that by the moles of the initial substance to get the moles of the other substance. Now, when it comes to gases, then we have to introduce, other factors such as the temperature, pressure, and so on. And of course, we can use the ideal gas law to find the number of moles of A, for example, if we know what the pressure, volume, and temperature are. So you might be given a problem where you're given the pressure, volume, and temperature for a particular gas. You can use that in the ideal gas equation to find the moles of one substance, and then multiply by the appropriate mole ratio to get the moles of the other substance. And depending on what the question is asking for in this case, you could be asked to determine not just the moles, but also the pressure, volume, or temperature, again, based on the ideal gas equation. So it's all a matter of the type of question that you're dealing with in terms of what you would use in the first part and what you would try to get in the second part. Okay, so let me move on to this example right here. So here you're given a balanced equation, and this is a reaction. I don't think this is used anymore, but they're talking about this reaction being used when you have an airbag deployed, when an accident happens and the airbag is deployed from your steering wheel in order to protect you from hitting your head or whatever, from injuries. I think they're using a different system now, but this is the system that this is the reaction that they used some time ago, where sodium azide will react upon impact to form sodium and nitrogen would be the gas that fills out the airbag. So the question is asking what volume of nitrogen measured at 25 degrees Celsius and 0.980 atmospheres is produced by the decomposition of 62.5 grams of sodium azide. So basically, I can summarize the question this way, and I hope that my pen is working properly now. I can summarize the question this way. You're given 62.5 grams, oh no, it's not working as I hoped, of sodium azide, and you're asked to determine the volume in liters of nitrogen at 25 degrees Celsius and 0.980 atmospheres. All right? So the first thing I would do is start off with the 62.5 grams of sodium azide. And then I would convert that to moles. So you're going to need the molar mass. So 1 mole of sodium azide will go above. And let me do a calculation of the molar mass of sodium azide. So nitrogen is 14.01 times 2, no, I'm sorry, 14.01 times 3 plus sodium, which is 22.99. So according to my calculations, the molar mass of sodium azide is 65.02 grams per mole, Na3. All right? So this will cancel out with this. So the next step would be the mole ratio between the sodium azide and the nitrogen. And as you can see, that's a 3 to 2 mole ratio. So I'd put 3 moles of nitrogen above and 2 moles of sodium azide below. so that this will cancel out with this, and you're going to end up with the moles of nitrogen. So let me do that calculation. 62.5 divided by 65.02 times 3 divided by 2. And the answer I got here is 1.44. 1.44 moles, all right, of nitrogen. So based on the moles of nitrogen and based on the temperature and the pressure, we can find out the volume by using this version of the ideal gas law, which would be V is equal to nRT over P, and then we put the numbers in. So the moles of nitrogen would be 1.44 moles times R, which is 0.0821, 21 liters atmospheres over mole Kelvin, times the temperature, which is 25 degrees, which we have to convert to Kelvin, so that becomes 298 Kelvin, all divided by the pressure, which is 0.980 atmospheres. And as you can see, the atmospheres units will cancel out here and here. Kelvin will cancel out here and here. The moles will cancel out here and here. So your final answer is going to be in liters. So let me do that calculation. So 1.44 times 0.0821 times 298 divided by 0.980. So according to my calculations, this works out to be equal to 35.9. Okay, where's that thing? 35.9 liters. Let me do that correctly. 35.9 liters. And that would be the final answer. All right? Okay, so much for gas stoichiometry. The next topic we're going to talk about is Dalton's law of partial pressures. Until next time.